All right. So while there are videos that exist for each lecture, things drift or, there's different questions that get asked that make it, exciting to that semester. But a question asked right before we started, EE 136 and EE 129. 129, how transistors are made, right? What feeds into that is MADI 153 device. It's really device physics, and then EE 128. But you only really need this one to take the course, right? And you make transistors. And you got a taste of that if you had MADI. If you're having MADI 153 this week, you're getting to get a taste of some testing. Right? It was like a reunion last night. EE 136, yes, it's power electronics, right? But what might not come out of that, it's power analog electronics. And if you're going to be an analog, right, you might think, well, that's somebody who designs the op amp or designs with an op amp. But power electronics is analog design as well. And you need to really be intimately familiar with all the properties, where chances are of a transistor, of a semiconductor, while you're getting a good foundation in MADI 153, you really end with the diode and a solar cell. So for me to tell you what the properties are right now wouldn't help. Okay. But yeah, 128, 129, they can be taken at the same time. Right now, 129 is only offered in the spring, and I think maybe 136 is offered in the fall. And when I say it makes a good pairing, yeah, those together would help you in an analog career, right? Now, yeah, to learn how to design an op amp with professional tools would be EE 223. Digital is 224, right? And, that's like a path, right? And then there's other courses that you can, surprisingly, EE 178, which is hardware design. You actually get into a lot of the full custom design things where the device physics are really important. And so when I started, yeah, these were very popular, but then, even the dean at the time, that's all going to Taiwan, nobody cares anymore. And yeah, enrollment in these courses did go down. However, it is really hard to learn this on your own. In fact, just talking to Naomi, you know what, I'm going to quote you the way I wanted you to say, is like, it wasn't really until I was in in that MADI 153 lab learning how this is really done to where it made sense. Is that accurate? Okay. I had an aunt that would just tell you, like, this actually wasn't so bad, but I'm going to tell you this story the way I want to because it's more exciting. Okay, and usually, yeah, anti local government tirade is usually what happened after. So anyway, um, yep, undergrads can take grad courses. You don't have to be in Sage. Um, just leave it at that. Okay. So, um, what I want to do, let's see, is go back to the time domain. Let's just do, kind of the base thing. So yeah, um, after I redid the course a bit, we have time to actually review, right? So now would be the time to be going over the problems from midterm 1 and 2 because just to get it back in your head, because doing it the night before or even the week before is going to be too hard. So what I want to do in class is to go over a problem a day. All right. So of course, you probably see where this is going. We want to do the convolution of this, right? And the thing is, yeah, we haven't seen it in a long time, but today, as we go over an example you've seen, you might really have an aha moment. Like, oh my God, is that what was going on the whole time? This is so easy. Okay, that's not gonna happen. But but like having your confidence jump up, I think is something that could happen. So again, one should kind of plot this out, right? So that you can sketch what's going to happen, regardless of whether you use the Laplace transform or time domain, because we're going to break it up anyway and scale and delay. And, you know, so let's do h of t. And yeah, it's a little hard to draw the delta at 0. So I'm just going to put like 1, right? Because when I integrate over that, I get 1 because it's infinitely thin and infinitely tall, which I can't draw, right? And then I'll choose a different color. We have this decaying exponential, right? That at 5, it's effectively 0. Now, this is going to be a smidgen hard. This is where it's going to be a little more difficult to draw because I cannot draw it on the same scale. But I'm going to draw G over here, and I'm just going to draw a tallish, thinnish rectangle. And the rectangle is 100 units tall. And just notice how cleverly I've done it. I have the step function here minus step function minus 1 over what it's scaled by. And so that means it's a 100th wide, right? And some things that I think now can be easily pointed out, right, is that the area, right, the width is 100, 100th, the height is 100, it's 1. And that makes it really easy to find out what the final area and all things like that are, right? Now, you might not see it, but the area of this is 1 as well. Okay. And if I do call this 1 over RC and this 5 RC, that'll hold. All right. Now, we're just going to scale and drag. But notice how thin this shape is, right? So I'm just going to draw it over here. But whatever this shape is, convolved with the delta function, right, is going to give me that original function, which actually, I need two hands to draw. Now, I also have this, right? And this one you might think of as a bit of a trick question, is that thought bubble, that's the word. I'm going to come over here to the thought bubble, where I'm going to draw this, okay? But remember, this has an area of 1, right? So if I'm passing this over, it's so tall and so thin that I'm effectively getting, I'm not scaling it in time right, but I'm getting that shape, okay? Because it's almost like a delta function, right? So it's still going to be minus, but again, it's so tall and so thin, I can just almost draw it almost as is, right? And then this is a delta function. You get in the same thing, okay? And yeah, you would just sum it. So, that's like 100, and this is 1, right? So my ultimate plot, I think, again, this one's a little bit hard because this is 100 and that's only 1, right? But I should get something like this, which was like the original thing, meaning this is so tall and thin, it is acting like a delta function, right? If I were, I can't draw on the board. So let's just make this, right? Call this 100 high, right? And the width of the line 100th. Now, yeah, is that really to scale? I would have to do, one width, two width, just kind of count how many widths. It's that hard to draw, right? So if this is 100, okay, one of those, I mean, you can barely even see this, right? So so it's really, and remember, you can see this delta function, but not really. It's just infinitely tall and infinitely thin, right? So as you pass it over, you would just look at this and say, oh, that's just a delta function. I can just draw the thing. all right? Which might be, a trick question, but I think it's a good time to realize that. So then, so really we have some functions. We have UT convolved with delta, and we have UT convolved with e to the minus t, all right? Well, this is by inspection, right? UT, delta t, you just get UT. And the step function, right, that's just like the low pass part, which you can look up either way. Myself, um, I have it memorized, right? Right. So let's just call this Z1 and Z2. Oh, wait, that was causing confusion. F, let's call it C1, common 1, common 2, because Z might make you think of 112. So common 1, common 2. Great. So now I look at this and I have UT convolved here, UT convolved here. So I have common 1. There's the scaling I'm going to leave for later, but there's no delay, right? Now I have a scale. No. Now I have now I have this one. It's scaled by minus, right? It's still common 1. I don't know why I'm making that a T. Apologize. But there's a delay. Okay. So this involved with this involved with, the minus sign comes here, and the delay comes there. Great. Now we have the other convolution. Um, so we have minus common 2. It's scaled by minus, but there's no delay. Here we have minus times minus, it's so scaled by plus 1, but there's a delay of minus, wait, yeah, minus 100. And then I can go back and scale the whole thing by 100. Okay, so the first common one is just UT minus UT minus 100. Now this one could get like somewhat trickier, right? Then I have common 2, no scale, I mean no delay, so minus 1 minus e to the minus t ut plus 1 minus e to the minus t minus 100th t minus 100th all by 100. All right. So this is true, but can we simplify it, right? So sometimes with these problems, right, the UTs can cancel out. So let's just, without having to redraw everything, this would be minus UT plus e to the minus t UT. All right. So that cancels this one. Okay. And yeah, we're still left with this. Yeah, yeah. And so then over here, right, it's UT minus 100th minus e to the minus 100th. And I'm running out of space. So I'm just going to say t minus, you know what I'm looking at, right? But now look, this, right, cancels this. And so now we're left with 100 plus e to the minus t t and minus e to the minus t 100th. Okay. So that does kind of have that other shape. Like if the rectangle was really long, right? Because this decays and then this one turns on, right? Because that's normally how I ask it. The rectangle is always 5 tau wide, right? You might have noticed that. But this is, let's just draw it out, right? This is doing this, and then this is doing the opposite, a little bit delayed, okay? Which, so it's delayed by 100th. So I don't know, it's just telling me that I'm getting a shape. This rapidly goes to 0, and then this is coming up. I think my graph isn't that great, and I would want to verify it, right? But if this were asked on an exam, right, because you haven't seen it before or something like that, I'd be looking more for the thought process. And did you at least get anything like this? Or really, hey, that's very close to a delta function, right? Meaning normally, yeah, I don't do process. But this one is a little more complicated, and I would be looking more for process. Now, I see you, and I'm gonna talk to you in a second. But on the other hand, right, if you do rectangle with longer rectangle, well, no, I better get a trapezoid, and the trapezoid is the width of this plus the width of this, and you know, if the area is 1, then the area, this goes to 1, right? That's a simple one you should be able to knock out. But if there's something not quite right, but recognizing that there's shapes that go up and stay up, right? Right? Which what it is it's once it starts integrating, it never stops, right? And then there's shapes that go up and come down from 0. So what it is this will integrate to a point, right? But then as it passes a shape, could conceivably stop integrating, right? And so we have shapes, like this, okay? Um, so if I have an up and down shape convolved with a shape like like that, right? It'll start to integrate. The areas will overlap, so it goes up, but then at some point it's completely overlapped, and it doesn't matter where it is, the area is constant, so it flattens out, right? So for this function here, the shape of how you get there will change, but since it goes up and comes down, and this doesn't come down, when you convolute the areas, it'll stay like that, right? Now, yeah, if you have a shape, I could have a shape that goes up like that, a shape that goes up like that. Well, if I convolve this, yeah, there'll be a region where it's starting to overlap and it'll increase, but then this will always be overlapping, the area will always increase, and it will never go back to 0, right? But at no time do these ever go less than 0. Now, yeah, there is a high pass to a rectangle will do this, right? But just remember, and then after this, I'll answer your question. UT convolved with e to the minus t, UT is not UT convolved with this plus UT convolved with this, right? This is all, that's all one unit, right? You see mathematically it doesn't make sense. But this expansion is like a mistake, so that this would then become T, and then something happens, and then people will do, I don't know, it's this shape. Now, I probably could ask a question that would come up with that shape for real, but I'm not going to. So I usually don't like to show how not to do things, but this one comes up and came up a little bit this semester, so I mentioned it.
What goes up must come down.
Yeah.
Logic, everything.
Well, what I would do is even though you can't bring a cheat sheet, is like, what are the shape, like you have delta, step, and ramp, and then you have it to each other, right? Well, the delta just repeats whatever you have. So really, you have these two shapes, and if you convolve them, right, the area continues to increase, right? And so, you know, this, yeah, it'll be linear, always goes up. If I do this, it'll go up, squared. And if I do this, it goes up, uh, what is it? 1/6 UT, right? It always goes up. And so if you see, something like that, well, it doesn't flatten out. Oh, it flattens out here and here, but at the end of the day, it's going to keep going. For those of you watching the video, that was me taking my arm and pointing to the sky. So now you have shapes that go up and come down, right? Okay, well, you can do that with the step, you can do that with the ramp, you can do that with this, right? And so here, the area actually flattens out, but in this case, as you're moving it, right, first you have that overlap, then that overlap. The area is actually increasing because it's going up. Same here, right? So even though this goes up and comes down, with these, right, the area is increasing. But when I have that shape, it could be that shape. It could be reverse triangle. It could be, you know, that. I don't do reverse exponential, right? But, once you have that and it's just, does it go up? Does it come down? Right? And then when you multiply it, multiply by each other. So you can just very quickly, what's the shape? And plot it out like that and not even, so at least you know you're in the right ballpark. Okay? All right. So there are, I have like sample exams, some with answers, some without, right? So the Fourier expansion, right? It really important. But if I take some signal, right, that repeats forever with a fundamental frequency, I can turn that into, you know, a sine wave with a sine wave with the fundamental frequency, right? But then there's also cosines that can be present as well, right? But then not just at the fundamental frequency here, but then I'm going to put an n there, right? Higher frequencies. N can be, one is the fundamental, but two, three, four. And sometimes when you derive it, not everything exists, right? Which then makes it easier. Plus you have sine 2 pi n t, okay? And then this would be, oops, sorry, B1. This would be A1, A, AN, and BN. And so these are all different constants depending on which value of n you are, right? And you just sum these up, right? Um, so here's this signal in time, right? And you can convert that to sines and cosines of different frequencies and different scaling constants. And then there's another form where it's just a cosine, but you're adding a phase term. So if you have no phase delay, right, you just have n, and your constants here. And there's something called A naught, which we'll spend some time. And it's really just the average, DC average. All right. So if you think about it, right, well, how will a low pass filter react to this? Well, I could do it in LT Spice or something like that, but there's frequencies. I can break this up into frequencies, right? And then decide, and and then everything we've ever done with a single frequency operates across the whole spectrum. So let's just do something, okay? Let's do a pulse that starts at 0, goes to 1, and yeah, I'm trying to get a square wave. So I'm going to do like 1 nanosecond rise and 1 nanosecond fall. I want it on for half a second, and I want the period to be a second. Oops. And like 10 periods. Okay. Now, the rise and fall time aren't really a nanosecond. LT Spice will adjust it for speed. If you really want it to be a nanosecond, you have to set the simulation time less than a step, less than a nanosecond. But, that's going to take too long. All right, so let's just see what happens. Let's look at the FFT, which is a digital algorithm, right, for finding these things. Now, in lab, you would have done some of the waveforms I'm giving you are for continuous time, and they have analytical solutions. But really, if you want, take a song and then try to use the analog techniques to get it, no, it'll take forever. So if you want to know the frequencies of a song, you just use a Fourier transformer, otherwise known as a spectrum analyzer, but it's mostly done digitally now, right? They used to have analog ones, but so let's see what happens. Okay, so yeah, interpreting this. So you can see at 1 hertz, I have a peak, right? But what's all this in between? Well, it's noise. Now, how do I know that? Is, I look and say, well, this is minus 10 dB, and over here it's like minus 90. Well, I can see it, but only because it's on that kind of a scale. So if you actually put it on a linear scale, well, that kind of goes away. Because when you digitize it, there's artifacts that just come out, right? And we have a peak here, and then interesting, we have a peak at 1 hertz, 3, 5, 7. So remember, I said n can equal 1, 2, 3, 4. But if n is 1, I get a hertz. N2, there's nothing there. N3, there is. And you can find that you can mathematically find the Fourier expansion. Now, something else in interpreting this is this is RMS. So you might calculate, we'll just go back. For this square wave, you might calculate B1, right? Then you go in LT splice and it doesn't match, right? And that's because this is an RMS. So if you really want to see it, you have to convert it back. All right. And now that's 0.63 volts, right? And there is an analytical equation for that. But if it's not matching, yeah, it's because it automatically comes out in RMS. And by multiplying it by the square root of 2, because remember, it's all sine waves, right? Um, so it's a way to check your work. But let's say this is a well-known signal, right? The shape is well-known. But let's say I have this signal. I want to know what the frequency components of it are. Okay. Well, now I can see the frequency components. Now I can decide, what if I want to get rid of something? What if I want to keep it? I've been having trouble with this program, so it might not do what I want. If not, that's okay. Yeah, sure. Mhm. Okay. So now I know what's there. And maybe I say, I want to get rid of all these frequencies. So I can just kind of draw a shape, high pass, right? No, that's keeping all. I want to keep it all. Sorry. And so if this is 0 dB, right, in the linear scale, it's 1, V out equals V in. And so if I have a high pass with a cutoff frequency here, the 1 hertz, everything just gets multiplied by 1. It's there. But let's say I want to get rid of that. Now again, I'm drawing a Bode plot in dB on a linear axis. You know what I'm saying? It's not strictly right. Okay. So now I've done a low pass filter with a cutoff frequency of around here. And that means, now remember, this line goes down. And so if this was at, minus 40 dB, oh, well, what would happen here? I would have 630 times 10 to the minus 40 divided by 20. That would be the new sine wave. It would be attenuated. And then this is, it's not a decade, but it would be smaller, right? And a first order filter, right, would go down by 20 dB per decade. So there is some of this signal coming through, right? But the higher the frequency, the more of it's attenuated. This frequency is, when we're doing the pulse width modulated DAC, is the one you're really trying to get rid of. And so you might want something sharper. Again, it never goes to zero. So now, the way I've drawn it, I'm trying to draw it so that it's lower. You know what? I'm just going to have, right? And so if I have a first order, that's my attenuation. Second order, it'll be lower, and so on and so on. Let's say I want to keep just that filter. Oh, I would put a band around it. Again, it's just a sketch, right? So now everything else should be attenuated, right? And let's say it's coming 210 millivolts, but I want it up to 1. Well, then I would have a bandpass with some gain. It would make it bigger. Let's say I want to get rid of this one. Okay, you do notch. All right, band, get rid of high frequencies, low, pass them, high. And that's, so when you have some unknown signal, right, you can take the FFT, see what frequencies are there, and then start to manipulate it. But just as a quick thing, if you've ever had a stereo graphics equalizer, showing you all the frequencies of the music through time. So the peaks are going in time, right? Every time a drum goes, right, boom, the low frequencies go, right? This is not showing you how it changes in time. It's just there. So as you put a slider to make more bass, yeah, it's a bandpass filter when you're increasing the gain for that frequency or decreasing the gain. But you don't, now, yeah, I don't know, like the sound system on my TV, it's like more bass. It doesn't control it frequency by frequency. Maybe so it bumps it up. So it might have a band of frequencies low, band of frequencies high. But that's kind of the big picture. And with the pulse width modulated DAC is a square wave. It comes out of a microcontroller with one pin. So this is a digital signal, but how long it stays on is actually like an analog signal. How long is it on? Is it on all the time? 50%, 25%? That's changing in time. That's where the information is, but it only takes one pin, right? You don't have an analog to, digital to analog converter on the chip, which can, it takes up area, costs money. Now, yeah, if you went to the PSOC thing the other day, yeah, they have A to Ds, D to As on that kind of thing. But if you're looking for the cheapest microcontroller you can find and you kind of need an analog signal out of it, well, pulse width modulation is certainly a technique, all right? But you have to get rid of this part. So you need a filter that is getting rid of as much of the AC as possible. It never goes to zero, right? It's always there and it comes across as a ripple, but you just say, here's a specification and you just design from there. So that pulse width modulated DAC, right, it has the Fourier, it has all the filtering we've done. In order to do it, you need op amps, and it pretty much ties together everything we learned in 110. Now today was just like a kind of an overview, right? I haven't told you how to calculate anything, you know, but um, and yeah, I should have done this first because you already had it in lab. And I changed the due dates in Canvas, but forgot to switch it in the notes. So I went straight into controls. So I have to change the Fourier due dates to later, but I'm hesitant to change the control due dates to earlier. So I'm just going to leave them be, right? But the sooner you do it, the better it is for you, right? But some people, they're very organized and their schedules are very tightly controlled. So I'm not going to change. I'm not going to up a due date on you last minute, right? But be aware, you probably should have all those controls done this weekend so that you don't, you know. Anyway, but yeah, I have to change the Fourier uh, due dates, and I apologize for that. But that's quite a bit. Any, actually, ask a question that I asked at the beginning of the semester. Does anybody use this at work or a hobby or anything?
Well, I've used PWM to do like servo control,
Okay.
so basic, but yeah.
For company, hobby, or if
Just hobby.
robot? Okay, robots. Um, yeah. Okay. You have a spectrum analyzer? Hold on. You're not coming through. The ATLM, well, here's the thing, as you know, the ATLM 2000 that fits in the palm of your hand is a spectrum analyzer. You've probably done that already. I forget her next hand.
I installed car stereos a little bit. I installed car stereos.
Okay,
I use Fosgate software to control signals all the time. Because
cool.
sometimes some components come up bad and we have to return back to the store. Um, it
Yeah.
control the proper bass of for certain customers. Some people want extreme amounts of bass that can hear from a block away. And then some people want quality sounding decent sound compared to like car manufacturer.
Okay, yeah, yeah. Was there another hand? Oh, I didn't know if you were like, hey, I didn't know if you, okay.
We use this to know if it's like a high frequency short when you're designing the ground to make sure the current actually goes through the ground and there's not a high impedance. Make sure that your ground leads have lower impedance for the frequency.
Wow, that's a great example. Um, so I'm not quite sure why that's still showing up, but So the thing is we talk about ground all the time, right? It's this perfect thing. Not. So let's try. I'm going to try to draw a schematic and like a real world thing at the same time. So, yeah, a nodal analysis, this is all the same voltage, right? Which is a lie. So imagine I've drawn it thin like a wire because it is a wire, right? And in fact, wires have inductance, they have resistance or conductance, and then now I forget, and you can have a capacitance. And you can take this and repeat it and make the inductance and the resistance and the capacitor so small that you can actually approximate this real world electromagnetic, physics 51 thing in LT spice, right? But this is a real wire. And so just think about it. Inductor, capacitor, resistor. Let's just call that filter, right? But we really want this to be the same voltage for every frequency. And what Joe's talking about is that for high frequencies, it might not be ground. It might be just, it might be acting, um, well, if I have a low pass filter, high frequencies are going to be attenuated and it won't bring it down to ground the way you want, right? And so what I think he's saying is he's looking at these frequencies, right? And these are like evenly distributed. And I can look at the before and the after. And if the input and the output have the same frequencies, well, it's acting the same. But if these are missing, that means they're probably being grounded. It all see, now you're trying to make this. All right, this is the thing. As I have ground here, right? And then I have ground here. But if I put a voltmeter from here to here, I'd say, what's the voltage? And you'd say 0. No, because you've got this kind of quasi filter impedance really there. And at different frequencies, these voltages will not be the same. So you want everything to be, you want this resistance here to be 0 for all frequencies. So if I'm noticing frequencies from here to here, they're not passing, and that's one kind of non-short, the opposite of what, and then if the low and so you can go from there. But yeah, that the other thing that this can be used for um, is that you have solar panels, right? And that's effectively DC. Yes, it is AC as the day goes on, right? Goes on, it goes off, on, off. But for moments in time, right, it's DC. But if you want to transmit it, you got to convert it to AC. And what you do is you have an oscillator, many times a square wave, right? Converting it to a frequency, which then you can bump up the voltage for easier transmission, all right? And that square wave causes something, they just say harmonics is bad, right? And my nephew works for a power company, and yeah, people are putting on green energy, and then the grid can't handle it because everything's assumed to be like 60 hertz, and it's not. 60 hertz sine wave. No, it's practically a square wave. And the thing about these harmonics, let's come back here, is that yes, it's going towards zero, but let's go back to the decibel scale, okay? So for a 1 hertz square wave, we can see elements at 10 kilohertz. So when you design your thing around 60 hertz, right, and all of a sudden you multiply that by 10K, right, it can stop acting the way it's supposed to. Things can heat up because it's not filtering. And so it does, you have to manage it, right? Thus, electrical engineers will always be needed, which is the important part. You might have thought I was going anti green energy, but it's just some of these things are hard to model. And yeah, you might say, why is PG&E on everyone's case about solar cells, right? Well, because it does play with the grid, right? And they have, but how much does that really cost? I don't know. I can't comment. But yeah, he had asked me a question like, I'm noticing this shape. What do you think it is? And I'm like, well, I just know that DC to DC there's a square wave, right? But if you look at let's see, LT space. That's a good. Let's go back here. Add a part. Compare current, contribute to filter, power products. We used to use this part in 122. Let's see. Analog devices bought them to show their parts. $31.05. There we go. Or I could just look up the old lab manual. All right. LT T 3105. Open this text fixture. Okay. Hmm. So, so this 1/2 volt power supply, it's really supposed to be a solar cell, but it's easy to model, right? So you just put that in there. But here's that you need this inductor so that you can have this oscillation. So let's just look at V out. Okay. So it's kind of turning itself on. Like it starts at 0 and now this is its output voltage. All right. Now, if I zoom in, okay. Now, well, I really don't want that part, but it's okay. I'll let it go. I can do the FFT and it'll do it just on the window, right? It won't give me the whole thing. Okay. So if I do view FFT, right? Um, Somewhat hard to interpret. I'm just going to try linear. So yeah, um, by the way, LT Spice gets rid of the DC part, but I've got a component at, I don't know, less than a kilohertz. So I'd rather, I don't like the analysis. So I'm going to run the simulation longer, but save it so that initial 3 milliseconds isn't going to show. So simulation command. So I'm going to go for 10 milliseconds to try to get more data, but I'm going to save it after 4. That way I don't have to worry about it. Okay. Nothing's happening because it hasn't gotten to 4 milliseconds yet. Actually, I could just, oh yeah, here it is. Simulation time. So it says it started at 0, right? But remember, I'm saving the data after 3 milli. Okay. And now this is it's simulating now, right? So if I went for 10, started saving at 3, yeah, I should get 7 milliseconds of simulation time. Notice this takes a long time, all right? Because the switch is going much faster than the simulation, than the bigger, like the time to charge is long, but the switch is going very fast. And so this is why LT Spice was originally called Switcher CAD, because they were trying to come up with a faster way to simulate their power supplies. All right. But you can see, yeah, it's going from what, 4.07 volts to 4.122. Okay, but it looks like that's a terrible thing, but it is small in the grand scheme of things. But but now you can really see the harmonics, right? We have a fundamental so by taking more time, we were able to get a better picture, right? So we got a fundamental frequency at 10 kilohertz, right? And then these are, even if we go to linear, right? Yeah, so there is a lot of high frequency data that if you have this is, this solar cell in this case is like this big, okay? But imagine a house putting that on the thing, or yeah, now you need to have better filters on the house. And you might say, well, just add some capacitors. Sure, but you have to have capacitors and resistors and inductors that are very ideal. Otherwise, the filters really won't work, right? Um, at the end of the semester, you will do an RLC filter, and you'll see it filters great, and then it not stops filtering, all right, at higher frequencies. Uh, Hold on. You can't see my hands move in the air. So what I'm saying is, Butterworth high pass RLC filter, right? Should do that, right? But the components are not ideal, and so it'll do this, okay? So this is cheap. This is expensive, right? Um, and so that, and then yeah, now I really don't know. I think wind is generated probably at a different frequency than the grid needs, but I don't know off the top of my head. But that, yeah, that will cause an issues that um, can cause headaches for the grids. But the people selling you the solar panels don't care about that, right? They just want to get it on your roof and walk away. They don't care about the grid. So this is where IEEE setting here's the standards that home solar installations should have a total harmonics less than this at this frequency range. Like, the Wi-Fi standards, those are IEEE standards. Okay. Uh, Next time, we're going to go over identifying the fundamental frequency, finding the average, and like kind of intuitively finding the Fourier expansion. Because really, you're not going to have an exam where I give you some random function and you will calculate it, right? What Professor Morelos needs from you in 160 is find the fundamental frequency, the DC offset, and some other things, right? But also, I think you do this in 112 too, right? People do well on this subject, so I'm not going to beat it to death. Any questions? All right, guys.